Hello everyone, welcome back to the algebraic graph theory seminar. Today, Signe Lundqvist will tell us about Euclidean and projective rigidity of hypergraphs. Signe, please.
Yes, hi. Thanks everyone for coming and thanks for inviting me. So my name's Signe. I'm a PhD student at Umeå University, and I work in an area called rigidity theory. So most of this talk would just be an introduction to different notions from rigidity theory, with obviously a bias towards the problems I've been working on and and I'm currently working on. Okay. But we're going to start with, so this is an outline of the talk, and we're going to start with just rigidity of graphs, which is sort of the most classical setting for rigidity theory. And in the classical problems, what you have is just a simple undirected finite graph. So a set of vertices and a set of edges, pairs of vertices. But rigidity theory it's fundamentally about geometry, right? So what we do is we draw these graphs in the plane. And if you have a finite, simple, undirected graph, drawing the graph in RD, so d-dimensional Euclidean space, just amounts to mapping your point somewhere in Euclidean space. And then you can see the edges as just the unique straight lines between the vertices. So a framework in the plane is something like you can see on the slide. That's a framework of K4. Okay. And then what we're interested in is whether or not these frameworks are flexible. So this framework here of a square is flexible. And flexible means that it has a motion which preserves the edge lengths, but which is not just a transformation of the underlying space. So it's not a rotation or a translation. All right. So to repeat, a continuous motion of a graph framework is a motion of the vertices, which preserves the edge lengths. And every single framework that you can possibly draw in the plane can be translated and rotated. And in higher dimensional Euclidean space, you have the Euclidean motion, or the rigid body motions, just the transformations of d-dimensional Euclidean space of any framework. And so we say that translations and rotations are trivial continuous motions of a framework. And a d-dimensional framework of a graph is rigid if all continuous motions of the framework are trivial. Otherwise, we say that it's flexible. And we say that a framework is minimally rigid if it's rigid, but removing any edge makes it flexible. So the K4, the K4 framework here is rigid. Since every pair of vertices is connected by an edge, any continuous motion of the framework will have to preserve the distance between any two vertices. So it will have to be a translation or a rotation, or a combination of them. But actually, the framework in the middle here, so it's a square with a diagonal, is also rigid. And in fact, that framework is minimally rigid, because if you remove any edge, if you remove the diagonal, if the edge you're removing is the diagonal, then you will get back to this square, which we saw was flexible. And if you remove an edge in the kind of outside force cycle, then one of the vertices will be able to move independently of the rest of the graph. So that one is minimally rigid. And the square we saw was flexible. All right. Any questions at this point? No. Good. Okay. So in practice, it's easier to consider linearizations of continuous motions, which we call infinitesimal motions. So technically, what you have is an assignment of a d-dimensional vector to each vertex, so that this equation is fulfilled this is just denotes the scalar products of two vectors, and that's supposed to be 0 whenever the pair of vertices is an edge. And the infinitesimal motions are elements of the kernel of an E by dV matrix. And it has rows of this form. It's actually the Jacobian of a quadratic system of equations. And it has rows of this form, so it's non-zero. So the row corresponding to an edge is non-zero only in the D columns corresponding to the vertex V, and the D columns corresponding to a vertex U. And in the D columns corresponding to the vertex V, you have corresponding to the vertex V, you have these, and in the vertex corresponding to U, you have the negative of that. Okay. All right. So if D is equal to 1, so if you're just on the line, then the rigidity matrix is actually, it's an oriented incidence matrix of the graph. So you have an E by D matrix, which is, so the oriented incidence matrix is just an E by V matrix where the entry ij is, the entry EIVJ is 1 if the vertex V is on the edge, or so you have a directed graph here, and if the edge EI starts at VJ, then the entry IJ is 1, and it's -1 if the edge goes to VJ. Otherwise, it's 0. And for D equals to 1, you just have an E by V matrix, which is some constant in the column corresponding to V, and some constant corresponding to U if the edge goes between U and V. Right? So it's actually up to scalar multiples of the row. This is an oriented incidence matrix. And in higher dimensions, it's sort of up to permuting the columns. It's it's sort of several incidence matrices. D copies of the incidence matrix. All right. So going back to the infinitesimal motions, again, you're going to have linearizations of trivial continuous motions, which are infinitesimal motions for any frameworks in RD. And a framework is infinitesimally rigid if it only admits trivial infinitesimal motions. Otherwise, it's infinitesimal flexible. So if a framework of a graph is continuously flexible, then it's also infinitesimally flexible, but the converse is not true. So if you look at these frameworks of a triangle, then 2 of them, so this one and this one, they're continuously rigid and also infinitesimally rigid. But this framework here, where all the points are collinear, has an infinitesimal flex, a non-trivial infinitesimal flex. Okay. But this is kind of, the framework where all 3 vertices are collinear is kind of special. And that intuition is kind of true. So given a graph, either almost all of its d-dimensional frameworks are infinitesimally rigid, or almost all of its d-dimensional frameworks are infinitesimally flexible. So this justifies talking about rigidity and flexibility as a combinatorial property of the graph, rather than about the specific frameworks you're looking at. And even more precisely, a d-dimensional framework of a graph is generic if the coordinates of the vertices are algebraically independent over the rationals. And in particular, all generic d-dimensional frameworks of a given graph will have the same infinitesimal rigidity properties. So they will either all be infinitesimally rigid or infinitesimally flexible. And we can say that our graph is infinitesimally rigid in dimension D if all of its generic d-dimensional frameworks are infinitesimally rigid. And for generic frameworks, continuous rigidity and infinitesimal rigidity are equivalent. So what you can say here is that this rightmost framework, the one with all the vertices collinear, is not generic, since you have the 3 vertices lying on a line. Okay. So if you recall that a graph is minimally rigid in the plane, if it's rigid in the plane but removing any edge makes it flexible. Now, the minimally rigid graphs in the plane have actually a combinatorial characterization, which is due to, it was first proven by Pollaczek-Geiringer in 1927. Then that result was kind of lost, and Laman rediscovered it in 1970. And a graph is minimally rigid in the plane if and only if it satisfies these 2 counting conditions. So if you think of just V vertices in the plane, then each vertex can move in has a 2-dimensional space of motion. So it can move in 2 directions. It can move up and down and in combinations of the 2. So if you just have a set of 2 V vertices in the plane, then they will have essentially 2 V degrees of freedom. But if you add an edge between 2 vertices and you say that the distance between these 2 vertices is no longer allowed to change, then you're removing one of these degrees of freedom. So what the first condition is sort of intuitively saying is that you've removed all but 3 degrees of freedom from these 2V. And the 3 degrees of freedom that you haven't removed, they correspond to a 2-dimensional space of translations and a 1-dimensional space of rotations. And they exist for any framework, so we'll never be able to remove those. And the second counting condition should just be interpreted as there are not too many edges in any subgraph. All right, so here are 2 examples of minimally rigid graphs in the plane. So I already showed you the square with a diagonal, but also K33 is also satisfies these counting conditions and is minimally rigid. Okay, and since this is a counting condition for all subsets of edges, it looks as though it might be exponential to check, but it actually isn't. There's a nice polynomial time algorithm to determine minimal rigidity of graphs in the plane. All right, you can always look at the corresponding counting conditions in higher dimensions, and then you end up with not too many edges in any subgraph, and also you have an overall count that needs to be satisfied, which says that you only have the Euclidean transformations of the graph. But these counting conditions in dimension D higher than or equal to 3 they're necessary for minimal rigidity still, but they're not sufficient. And finding necessary and sufficient conditions for minimal rigidity in dimension higher than or equal to 3 is it's maybe the biggest open problem in the field, because we don't have a characterization of minimal rigidity in dimension 3 and higher. Okay, so here's a vertex which satisfies these counting conditions for dimension 3, but it's not minimally rigid. It's in fact flexible because you have these 2 these 2 tetrahedra, these things. It's called the double banana graph, usually, and you have these 2 bananas that can kind of flex around the dotted line. So it's not minimally rigid, it's in fact flexible, but it satisfies these necessary conditions. Okay, so that's the first part of the talks. Any questions so far?
Is there some like basic structure you can add to the double bananas to make them rigid?
Yeah, that's a good question. So I don't think there is. So adding, if you were to add like an edge here, for example, Yeah, if you add an edge here, sorry, yes, if you add an edge here, between these two, then they would no longer be able to rotate independently. They would just rotate. It would just be a rotation, right? So if you add an edge here, it would be rigid.
Cool.
But I don't think that's not. I don't think that's like generally true of flexible graphs that satisfy the necessary counting condition. But for the double banana edge, there is, yeah.
So in some sense, this is maybe maximally flexible, or are there other edges you could add that would still leave it rigid?
So I think you could actually add any possible edge between the two triangles here. Will make it rigid. But if you add, if you add this edge, that will change nothing. It will still be flexible. Yeah.
Thank you.
Yeah. Okay. Any more questions, or should I move on? I'll move on to the next part, maybe, if there are no more questions. So the remaining parts of this talk will be about incidence geometries rather than graphs. Or so incidence geometries, they consist of a set of points and a set of lines, combinatorial points and combinatorial lines, and a set of incidences which prescribe which points lie in which line. And they're in fact perhaps more well known as hypergraphs. Or alternatively, you can think of them as by their associated bipartite graph, which has vertex sets P union L, so it has a vertex for each point in each line, and edge sets. The edge set is given by the instances. Okay. And to talk about rigidity properties, we need to have a geometric realization of these hypergraphs. And the geometric realization is often just a drawing of the incidence geometry as points and straight lines. So you can draw an incidence geometry in the plane by assigning a point to each element of the point set and a line to each element of the line set, such that if the point and the line are incident, then the realization of the point lies on the realization of the line. Okay, so it's these kinds of structures of points and lines. But not all. If you're thinking about hypergraphs, then it's pretty clear that not all of them will have realizations as points and straight lines. At least not if you require all points to be distinct and all lines to be distinct. For example, if you have an edge, if you have a pair of points that are incident to that have two common hyperedges, then you won't be able to draw those hyperedges as distinct lines. But even if you don't have that property, it's still true that, for example, the fauna plane has no drawing as points and straight lines in the plane. So we say that our drawing is trivial if all points are given the same coordinates, or all lines are assigned to the same line in the plane. Those sort of drawings always exist. You can always just map all of your combinatorial points to the same point, and then you can map your lines to any line that goes through that point. Or dually, you can assign all your lines to the same line, and you can just map your points to any point on that line. And we say that a drawing is proper if all points are given distinct coordinates, and that will and all lines are given distinct or mapped to distinct lines. Okay. So the first type of motion, I guess, for hypergraphs that I'm going to talk about is parallel redrawings. So in a parallel redrawing, you have an assigned normal to each element of the line set. And then what you're basically looking for is the space of drawings of your incidence geometry with those assigned normals or line slopes. to each line. And if you're looking for those drawings, you get a set of equations, these linear equations, where xi, yi, and hj are variables, and fj is the fixed line slope. And that's a system of linear equations that we can attempt to solve. All right, so I'll denote the coefficient matrix of the system of equations by M as rho. And it's an I by L plus 2p matrix. And a typical row, or the row of this matrix M as rho, corresponding to an instance Lj, Pj, looks like this. Right, so it's one column corresponding to each line, and two columns corresponding to each point. One of the columns corresponding to the point has the line slope fj, it should be fj, and the other columns are just one, and the columns that correspond to points and lines not involved in the instance are just 0. Okay. So this is also kind of almost the instance matrix of the well, either the bipartite graph associated to the instance geometry, or just there's a concept of an instance matrix for an instance geometry as well. And this is almost that. It has an extra column, but it's almost that. Okay. And the kernel of this matrix M as rho, it consists of the space of drawings of the instance geometry with the assigned line slopes. And this is the space of parallel redrawings of S with your given line slopes. And this kernel is at least two-dimensional because translating a drawing doesn't change the line slopes. So there are always two translations. And if your drawing is non-trivial, then there's also a dilation. Okay, but it's always at least two-dimensional, even for the degenerate trivial drawings. Okay. So the two-plane matroid is a count matroid on the set of incidences of an instance geometry. So a set of instances is independent in this matroid if and only if this count is satisfied for all subsets of the instance geometry. And the two-plane matroid, it characterizes independence in this matrix in the sense that the set of rows of this matrix M as rho, corresponding to a set of incidences, is independent if your line slopes are chosen generically, if and only if your set of incidences is independent in the two-plane matroid. So this is actually kind of a similar result to the characterization of minimally rigid graphs. That is also, you have a count, and that count corresponds exactly to independence in a matrix. Okay. And yeah, as I said, so translating and dilating any proper drawing of an instance geometry will give you another drawing with the same line slope. So the rank of this matrix is at most L plus 2p minus 3. Because the kernel is always going to have the dilations and translations are always going to be in the kernel of the matrix. And there's also a one-to-one correspondence between the parallel redrawings of a graph framework in the plane and its infinitesimal motions. And what this means is that the rank of this matrix mg rho, so if your instance geometry is a graph, gives information about whether a graph framework is infinitesimally rigid. So specifically, the graph framework is infinitesimally rigid if the kernel of the parallel redrawings matrix is three-dimensional. Okay, and the actual one-to-one correspondence just looks like this. So the blue vectors in the figure, they form an infinitesimal rotation, but this generalizes to any infinitesimal motion. And the red vectors here, they're the blue vectors turn the infinitesimal motion, so the blue vectors turn 90 degrees. And if you add those vectors to the points in your original framework, you will get another framework with the same line slopes. So basically, the one-to-one correspondence is just rotation in a consistent way by 90 degrees. Okay. And the good thing about this is that there's no assumption of genericity here. So this one-to-one correspondence works for any framework, including non-generic ones. All right, and we can also realize an instance geometry as a non-generic graph framework. So by defining a graph, by replacing each element of the point set with a vertex and each element of the line set with a tree on the vertices representing points incident to the line. And then you realize that graph so that the trees representing the elements of L lie on a line. So basically, if you have a line which is incident to the points P1 to PK, then P1 to PK should lie on a line, and there should be a tree on that line. And we call this a string configuration, realizing the instance geometry. So here, so in this picture here, you should interpret, okay, the black lines, they're just edges of a graph framework. And this red line should be interpreted as a path, for example, on these 4 vertices. But actually, the specific tree that you choose won't affect the rigidity property. So you can always assume that it's your favorite tree, for example, a path or a star. Okay. These string configurations are also characterized, again, by Whiteley. So an instance geometry has a realization as an infinitesimally rigid string configuration of the plane if and only if these counts are satisfied. And what these counts say is precisely that the rows of the matrix MS raw are independent, and that the kernel is 3-dimensional. Okay, and if you look at this string configuration just from the last slide, it satisfies these counting conditions and is minimally infinitesimally rigid. All right, any questions about this part? No. Okay, then I'll move on. So a rod configuration is kind of, it's the hypergraph equivalent of just a graph framework. So you have a drawing of the instance geometry. So a realization of your instance geometry is points and straight lines, and the lines move as rigid bodies. So here is an example of a flexible rod configuration. So the distance between any 2 points on a rod does not change in these motions. And here are 2 examples of rigid rod configurations. So here you can kind of argue that these are made up of, for these 2, it's quite easy to see that they're rigid because you can argue that they're made up of triangles. And you can kind of argue that there's no way of changing these angles in any way which isn't a rotation and translation, such that the distances are preserved. But it quite quickly gets more difficult. So does this rod configuration move, for example? The answer turns out to be no, it's rigid, but there's no easy argument to see that a priori. Okay. So just to repeat, a continuous motion of our configuration is a motion of the points and lines that preserves the incidences between the points and lines, and it preserves the distance between any 2 points that lie on the same line. And again, you can translate and rotate any rod configuration. So we say that translations and rotations are trivial. And if the translations and rotations are the only continuous motions of the rod configuration, it's rigid, otherwise it's flexible. And an infinitesimal motion of a rod configuration is an assignment of a vector in R2 to each point, such that if you restrict to each rod, you get the linearization of a trivial continuous motion. So you get either the linearization of a rotation or the linearization of a translation or a combination of the two. And the linearizations of the trivial continuous motions are the trivial infinitesimal motions. And again, if they're the only infinitesimal motions of our configuration, and one way you can model the rigidity of these rod configurations is by replacing each line by a cone over the point incident to each line. So a cone is what's in the figure here. So if the points A, B, D, and E lie in a line, then the cone vertex C is just a vertex outside of that line, which has edges to all points on the line. Okay. And this will give you a string configuration with the same infinitesimal motions as the rod configurations. All right, and for technical reasons, we choose the trees representing the lines to be star graphs. The one on the left here. Then what you do is a non-generic graph framework on the vertices on the rod, plus an extra vertex, a cone vertex. Okay, and this will have the same. A second way of realizing an instance geometry is by just replacing each element of the point set by a vertex in again, for technical reasons at least, the vertices representing points incident to the line. So what you've done then is a minimally rigid body on the vertices representing points incident to the line. And this is what's called a body joint framework, realizing the instance geometry. And these body joint frameworks are graph frameworks. So they come with a notion of rigidity. And another thing that you can note is that any framework of a cone graph is a body joint framework realizing the instance geometry, including but not limited to these frameworks where the points that are incident to a line are collinear. Okay. And Whiteley in the same paper that I referenced about the parallel redrawings showed a characterization for when an instance geometry has a realization as a minimally infinitesimally rigid body joint framework in the plane. And it's again a counting condition. So it's this counting condition here. It's equivalent to an instance geometry having a realization as a minimally infinitesimally rigid body joint framework. And that is also equivalent to condition 3 here, that your instance geometry has a realization as a minimally infinitesimally rigid body joint framework in the plane, such that all points incident to a body are collinear. So if we translate that to the stuff I've just talked about, condition 2 exactly says that the cone graph is minimally rigid, and condition 3 says that the cone graph remains rigid when the trees replacing elements of the lines are placed on an actual line in the plane. So statement 3 is actually a statement about rod configurations realizing the instance geometry being infinitesimally rigid. All right, and what we wanted to do, me and my supervisors, was to talk about which instance geometries have realizations as infinitesimally rigid rod configurations. And we wanted to do this in general. So Whiteley's result here requires your body joint framework to be minimally infinitesimally rigid. And we just wanted to remove the assumption of minimality, basically. Okay, so if you recall this a while ago, I stated this, I made this definition, but we say that our configuration is proper if distinct points are given distinct coordinates and distinct lines are distinct, then. And a major obstacle to actually generalizing this result is that if you don't assume minimality, then you can have instance geometries which don't have realizations as proper odd configurations. But okay, we can assume that they do, because we're interested in rigidity properties. So it's natural to assume you have a geometric realization that you're interested in. But then we want to be able to determine whether or not they're infinitesimally rigid. And to do that, we wanted to use the parallel redrawings matrix, M as raw. Yeah, we wanted to be able to determine which subsets of instances yield independent rows in this matrix. And to get some control over that, we made this assumption on the drawing, right? The assumption of regularity, where we say that a drawing is regular if the rows of this parallel redrawings matrix correspond to a subset of instances corresponding to a subset of instances I prime, are independent whenever this counting condition is satisfied for all subsets J prime of I prime. Oh, and L prime by P prime should be the support of J prime. Sorry, that's a typo. Okay, but basically this condition should be interpreted as the rows of the MS row are independent whenever they can be. They're as independent as possible. All right, so suppose you have a regular proper realization of a congraph of the instance geometry in the plane such that the trees replacing the lines are collinear. So basically you have a realization of, you have a rod configuration which satisfies this regularity condition. Then your instance geometry has a congraph which is rigid in the plane if and only if every rod configuration, every regular proper realization of a congraph of the instance geometry such that the trees replacing the lines are collinear is infinitesimally rigid. So in pictures, the congraph is rigid in the plane if and is rigid if and only if the realization on the right is rigid, provided that the realization on the right exists and is sufficiently generic. Okay, any questions about this part? Okay, well then I move on to the final notion of motions for instance geometries. Okay, you can also just make no assumptions on the points and lines in the drawing of an instance geometry. And if you make no a priori assumptions, then finding a drawing of an instance geometry just amounts to solving an equation of this form for each instance PL. And here A, X, B, and Y are all variables. And to define instance preserving motions, which we call projective motions, we differentiate the resulting system. We differentiate the system of equations of this form, one for each instance, to get a system of equations, a system of linear equations of derivatives, basically. So you get a system of linear equations that you can solve for A prime, B prime, X prime, and Y prime. So here you should think of A, B, X, and Y to be some fixed starting position. And X prime, Y prime, A prime, and B prime are an infinitesimal motion of this of this realization. So they're a derivative. They're actually what they technically are is they're elements of the kernel of the Jacobian of this system of I equations. All right, so you get a system of I equations in 2p plus 2l unknowns, and a typical row, or the row corresponding to an instance PL, looks like this. So you have 2 columns corresponding to each line, which should be filled with x and y. 2 columns corresponding to each point, which should be filled with a and b. And the rest of the columns should just be 0 in that row. Okay, and again, this is very similar to the this is kind of 2 copies of an instance matrix up to multiplication by multiplication of a row by a constant, or multiplication by columns by constant, I guess, in this case. Okay, so here we have an 8-dimensional space of trivial projective motions, which are projective transformations. So they're generated by dilations, shears, translations, and rotations. Of the coefficient matrix of the system of equations is at least 8-dimensional. At least 8-dimensional. So if these I equations are linearly independent, then you have to have this counting condition satisfied for all subsets of instances. And for the drawing to be rigid, by which I mean every projective motion is a projective transformation, then we also need the equality satisfied for the whole instance geometry here. Okay, so this here you may or may not recognize. This is a drawing of Pascal's. This is Pascal's theorem, basically. So Pascal's theorem says that these 3 points lie in a line if and only if these 6 points lie on a conic. Okay, and these 6 points on the conic, they're the vertices of a hexagon, and the 3 collinear points in the middle are the intersections of opposite edges of that hexagon. All right, and they lie on a line if and only if the six vertices of the hexagon lie on a conic. Okay. And if this conic happens to consist of 2 lines, then Pascal's theorem basically results in this configuration. So you have 3 points on a line. You have 2 sets of 3 points on a line. So you have these points and these points. They lie on a line, and then you have a hexagon on those 6 points. And then it follows from Pascal's theorem that these 3 points also lie on a line. Okay, and if you do a bit of counting, then the purpose configuration, it's one away from satisfying the counting condition for projective rigidity. So you would expect it to have a one-dimensional space of non-trivial projective motions, but it in fact has 2. Okay, so you can see here that this point between these 2 configurations, this point has just moved along this line. Okay, and these 3 points have also kind of moved along with it. Okay, but you also have that these 4 points the kind of corners, I guess, they're in fact fixed when you go from the configuration on the left to the configuration on the right. And it's a fact of projective geometry that the only projective transformation which preserves 4 points such that no 3 are collinear is the identity. So sliding this point along that line gives you a projective motion, which is not a projective transformation. Okay, and these 3 points in the middle, they will remain collinear throughout the motion because of Pappus's theorem. But I could just as easily have chosen to move this point, right? And in fact, I can move these 2 points just independently. Okay, so it has a two-dimensional space of projective motions. And that is a bit surprising. And it makes it hard to characterize projective motions. All right, because these counting conditions that I stated here, which are necessary for projective rigidity, they're not sufficient. And they're not sufficient because sometimes when you have these theorems, you get motions that you wouldn't expect. And characterizing incidence theorems is, or even giving an explicit description of what incidence theorems are, is kind of hard. All right. And that is it. So thank you for your attention, and I will take questions.
Thank you for the nice talk.
Mm-hmm.
Do we have questions for Signe?
Hi. So the difference between the two problems that you talk about, the rod configurations and these projective incidences, is that essentially in the second case you allow the points in the line to change distances between each other. Is that the only difference?
Yeah, exactly. So in this problem of projective rigidity, the only thing we care about preserving is just which points lie on which lines. And when we're talking about rod configurations, then the main thing we're bothered about, the main thing we want to preserve is, well, incidences for one thing, but we want to preserve the distances between 2 points on a rod. Yeah, so that's the difference between the two problems.
Thank you.